All right, everybody, welcome to the first lesson here. Chapter 1 we'll go through. It's very short and sweet. Now, with these lessons, I'm basically highlighting what I think the key concepts of the chapter are with you guys, okay? But I'm always going to recommend, and I'm always going to hold you accountable for actually reading, okay, in the ebook. This is not like a typical math book where, it's all real complicated to read. There's a lot of easy reads that go through the concepts we're discussing, lots of examples, so you can really get a good sense and understanding of the different things we're going to talk about, okay? So always read through the chapters. The lessons are what I'm emphasizing, okay? And then after these lessons, you should be able to go and chip away at some of the homework assignments on WebAssign, okay? If you end up with questions on anything, please feel free to reach out by email, reference the lesson, and maybe like what part of the lesson it was that gave you trouble, and I'll do what I can to help you out, okay? But here we go. Chapter 1, very straightforward, a lot of just kind of like basic definitions, terminology, some things like that, okay? So let's take a look. Key vocabulary. Well, first of all, what is statistics, right? What is this course we're taking? It's the scientific discipline that provides methods to help us make sense of data. Okay, we did some sort of a survey. We've got lots of numbers in front of us. Let's try to make sense out of these numbers and get some information about that population. Okay, in terms of population of interest, that's the entire collection of objects or people for which we wish to know something about. Okay, we want to know something about all undergraduate college students in New York. That would be our population of interest. Maybe we want to know something about all seniors in college in the United States. That would be our particular population of interest. In terms of the way we notate a population of interest in this course is the capital letter N. Okay, so if capital N equals 100,000, it means we're dealing with a population of 100,000. Okay. A census is when we have data pertaining to all members of the population of interest. The 2020 census is going on. That tries to make it to get information about every single American. Okay, where all U.S. citizens would be the population of interest. Okay, so a census data pertaining to all members of a population. In this class, we do a lot with sample data. Okay, a sample is a subset or smaller group of the population of interest. And kind of appropriately, the notation for the sample of a population is lowercase n. Okay, so capital N, the size of the entire population of interest, lowercase n, the number from that population that we're going to be included in our sample. A statistic is data obtained from a sample, often used to make generalizations back to the population of interest. And what you're going to find is, particularly later in the course, chapters 8, 9, and 10, is where we really start to kind of generalize back to the population of interest. It's like, what do we do if we've gone out and we've collected a bunch of data? What are we going to do with that data so that we can really get to know something about this particular group of people or things that we're interested in knowing about? Okay. Now, why do we use samples to generalize to a larger population, right? On the previous screen, we saw we could use a census. That's getting information for all people or all members of a population. Whereas samples, get subsets of that. Well, why do we use samples? Well, there's a lot of reasons. Okay, cost, of course, is a leading factor here. People, you have to pay people to conduct surveys and experiments, and the more and more people you get involved, and depending on what type of experiment you're running, and it can get very, very costly. Okay, so sample obviously will help limit that. Instead of reaching out to every member of the population, let's get a sample instead to save some money. Time is another factor, right? Suppose we were interested in the average length of a fish in the Hudson River, right? Hudson River is pretty darn long. How on earth could we go about catching every single fish in that river so that we could determine the average length of a fish in the Hudson River? That would take an extraordinary amount of time. A lot of times it can just possibly be impossible to collect data for all members of a certain population. In reality, can we catch every fish in the Hudson, tag and measure every single one? I don't know that that's a realistic goal. Another reason that we sometimes have to use samples is if we're destroying items, right? Think about it. Automobile companies do automobile crash tests. They're certainly not going to put every one of their cars into a crash test. They'd have nothing left to sell, right? Or companies that make batteries for your cell phones, right? Or batteries in general, okay? Or testing new fire extinguishers for effectiveness. Okay, these are things that after you use them, they have no more use left of them. Okay, so if we're destroying things, we have to obviously take a sample of these items to figure out what it is we want to figure out. We can't possibly use all of them. Okay, so in a general sense, it's often just not realistic to be able to get data for every member of a particular population for which we want to know something, but often we can get samples. Okay, so samples, easier to do. And then again, it's called inferential statistics. It's taking our sample data and then using that to make generalizations back to the population at hand. Okay. Another key word in the course is a variable. That's any characteristic or value that can change from one member of the population to the other. Some examples include eye color, right? I could ask all my students what their eye colors are, and I'm going to get varied responses: blue, brown, hazel, green, what have you. Okay. Number of siblings, that's a variable that changes from person to person. Maybe 0, 1, 2, 10, who knows? Okay. Height, the heights of my students, that's another example of a variable. Okay. And there are all different types of variables. There are three particularly that we study in this course. First of which is called a categorical. These are variables that describe characteristics of a population. They're typically non-numeric. Okay, they can be numeric, but typically they're not. Things like a person's favorite ice cream flavor. That's a characteristic. That's a categorical variable. Really favorite anything. Favorite teams, favorite sports, whatever. Hair color: brown, blonde, red, okay, black. That's categorical data. It describes a characteristic. Eye color, type, pet owned, dogs, cats, fish. Zip codes. Here's something that's numeric in nature, but really is categorical. Think about what a zip code or an area code really describes. It describes a geographic location. Okay, so these are just some examples of categorical data, things that look at characteristics. Okay. The other type are numeric variables, and within numeric there are two types that we study, the first of which is discrete numeric. These are thought of as isolated values along a number line, or counts of items. Discrete variables can only take on certain numeric values. Most of the time we will be dealing with whole numbers, but that's not always going to be the case. All right, if it's something we count, it's typically discrete numeric. All right, some examples: the number of siblings a person has. They could have 0 siblings, 1 or 2. These are specific numbers that are realistically a number of siblings someone can have. You're never going to have 3.5 siblings or 1.8 siblings. That just doesn't make sense, right? So there are certain numbers that not going to be included in the way we count the number of siblings. That's an example of discrete data. Okay. Number of credits that you're taking at UAlbany this semester. Maybe it's 8 or 12 or 15, right? You're never going to have 9.5 credits. A student's never taking 9.5 credits, 10.7 credits. Those are just numbers you're not going to see. Shoe size is an example where, it's not just whole numbers that are discrete, but there's only specific values that can be taken on. Someone might have a shoe size of 5 or 5.5 or 6 or 6.5 or 7. Nobody's going to have a shoe size of 5.76 though. That's a value that, between 5 and 6 is just never going to be touched. Okay. Only specific numbers can be hit. This is examples of discrete. And money. Okay. Cost in general, money in general, that's discrete. Money is, again, an example that's not always whole numbers, right? But you're not going to ever see a dollar amount that goes out 3 decimal places. A person might have $10.73, maybe they have $10.74, but they're never going to have an amount of money in between the two. Okay, these are examples of discrete values. Okay, only certain numbers can be hit. Okay, and to contrast that, we have continuous numeric. Okay, whereas discrete is thought of things we count or specific values on a number line, Continuous data is thought of are thought of as values along an interval or things we measure. Continuous variables can take on any value on a defined interval. They can be any fraction of a value. Okay, they can be they can just kind of go on almost forever in a decimal value. I'll try to explain in a moment, okay, what that means. Things like the weight of your books, okay, the weight of anything. Weight is a continuous measurement. Something can weigh, basically from just about 0 pounds all the way up to whatever pounds. It can be any fraction of a pound. Okay, and it's only kind of really defined by how accurate our measurement instrument is. But in reality, something can take on a weight of 4.999999877, and keep repeating pounds. There's no limit to how far the decimal can expand. Height is another example. Somebody can be 5 foot 10 inches, they can be 5 foot 11 inches, but realistically, they could be any fraction of height in between the two. Okay, and as you grow, as you go from being like say 4 foot tall to 5 foot tall, you're growing continuously through all those heights, through every fraction of a height in between. Okay, so it's kind of like my mouse here. It's like I'm this tall now, and then I'm growing to get to be this tall, and like my mouse didn't skip; it rose continuously. Okay, length of your arm is a continuous measurement. Okay, these are all things we measure: weight, height, length, volume, okay, volume of the water in your bottle, surface area of your cell phones. How big is your cell phone? Okay, the amount of time it takes to shower. Time is something we measure. Time is continuous. Okay, each of these measurements is only limited in accuracy by the tools we are using to do the measuring. In theory, any of these things could take on arbitrary decimal values, like I was talking about before. The volume of water in your bottle may be any value between 0 ounces and say whatever the capacity of your bottle is, maybe 20 ounces. You got a 20-ounce bottle of water, you've taken a few sips out of it. Well, how much water is still in that bottle? Well, it might be 12 ounces, it might be 13 ounces, but it could be any fraction of a number of ounces even in between, like some weird random number like this, which is only, and the decimal could even keep going, but, it's our measurement instrument that kind of limits how far the decimal goes. But in theory, we could have any amount of water between 12 and 13 ounces, right? And this is something we measure. This is continuous. So things, again, like weight, height, distance in general, volume of something, okay, surface area, time, these are all thought of as continuous numeric variables, okay? A little more key vocabulary here. Frequency refers to the number of times a particular variable shows up in the data, whereas relative frequency is the frequency divided by the sample size. This gives the percentage or proportion of time a particular variable shows up in the data. Okay. Maybe, as an example, what I typically do in class is I say, all right, how many of you have a dog at home? I'm a dog guy. I've got a dog. And maybe, I look at how many students raise their hands, okay, just to give you the difference between these two vocab words. So last I checked, there was 42 of you on my UAlbany as being registered for this. So I make 43. Let's suppose, that of 43 of us, a bunch of dog lovers in this class, maybe 31 of us have dogs. That would be the frequency. Okay, so suppose 31 of us have dogs. Okay, well, the relative frequency is just that divided by the total number of people. So that fraction represents the relative frequency. Okay, 31 out of 43 of us own dogs. Now, if you want to do the math and you actually punch that in, that is about 0.7209, and it goes on further and further, okay? But as a percentage, we're saying about 72% of those of us in this class own a dog. And that's what's meant by the relative frequency. So it's a fraction, which can be called a proportion, or a percentage. Okay, proportions and percentages are one and the same. And you'll hear me use those words a lot in this class. So we're going to get used to seeing percentages and fractions, proportions quite a bit. But anyway, just some basic stuff in this first lesson here. But believe it or not, this should allow you now to go into WebAssign and do some work. Okay, if you have any questions on this content, please let me know. Otherwise, hang tight, and chapter 2 will be up within the next day or two. All right, folks, have a good day.